So welcome everybody to the dissertation talk of Mr. Rezaul Karim. Rezaul worked with me over the last several years, in fact in FIT as well as here in RWTH, and I'm very happy that we are now approaching the final stage of his dissertation work. With here in the room is the dissertation committee. Consists first of all of Dietrich Reber-Schumann in here, so director of the ZBMed and professor at Cologne University, Bill van der Aalst, professor here at RWTH, and the chair of the examination committee, Professor Gerhard Lakemeyer, and myself. And with that, so we are streaming the event also in real time to the outside, so I see already that we have a couple of listeners there as well. And with that, I think I'm going to conclude and hand over to Rezaul, who will be talking about interpreting black box machine learning models with decision rules and knowledge graph reasoning. Rezaul, please take over.
Thank you, Stefan. Thank you, committee members. Thank you, audience, for coming here to see me interpreting black box machine learning model. So, in recent years, we have witnessed huge remarkable achievements of AI systems in computer vision as well as in natural language understanding and processing tasks. So in particular, deep learning models that are based on deep neural network architectures have shown tremendous performance improvements across very complex problems. Now, there are three main driving forces behind such advancements. So in particular, having access to large scale data, hardware accelerators like GPU and TPU that we have currently state-of-the-art data science and machine learning algorithms. Now, using such a hardware accelerator, we can now perform predictive modeling at a scale on such a large scale data sets in order to solve a very complex problem. So, although many machine learning algorithms, in particular deep neural network architectures, are showing increasingly higher accuracy at solving such a complex problem, but deep neural network architectures are increasingly becoming less and less interpretable. So compared to linear models or decision tree-like approaches, so although they tend to show lower accuracy, but they are highly interpretable. On the other hand, deep neural network architectures are getting like black boxes. So using black box approach, we don't know how certain input instances are mapped to certain output instances, so it clearly shows a trade-off between accuracy and interpretability. However, there are many critical situations where using such a black box machine learning algorithms are simply not allowed because of there could be practical and legal consequences. So to show what could be the practical impacts of using such a black box machine learning algorithm, so now I introduce two examples. The first example is to show the practical impacts of using black box machine learning algorithms in banking. So in particular, financial institutions like bank was one of the pioneers who started experimenting with black box machine learning algorithms for automating their daily business activities, for example, credit rating modeling. So the idea goes as follows. So once applicants submit their applications by containing information such as their age, their monthly income, as well as their employment status, then using a machine learning algorithm, so they basically compute the repayment capability of the customers, and based on the repayment capabilities or the probability, they take a decision whether someone's loan application has to be accepted or has to be denied. Suppose a customer, John, has applied for credit in a bank, and also assume that his loan application has been denied for some reason. Now, since customer has the right to know why this is the case, why his loan application has been denied, so the bank should be able to provide reliable justification. So what would be the minimal explanations or the justification in this case is, your loan application has been denied because of bad credit rating history, or maybe given your current income ratio, you are expending too much. So please try to increase your income and expenditure ratio, try again, and we will consider your loan application very positively next time. So this thing can get much worse in case of healthcare. So we know that in healthcare, AI is already contributing, providing significant contributions, in particular in order to provide improved healthcare, improved personalized care. For example, AI systems are already outperforming human experts, for example, like at spotting malignant tumors in order to diagnose cancerous conditions. But there could be several practical consequences in this regards. So for example, a few years ago, IBM had invested $62 million in order to develop AI solutions with the hope that the AI solutions would be able to improve and provide improved clinical diagnosis and prognosis recommendations. But it turns out to be a complete failure because their AI systems not only made wrong diagnosis recommendations, but also multiple erroneous therapy cases were reported that put patients' life in a dangerous situation. So unless we don't know why it was the case, why such an AI systems made such a wrong diagnosis decisions, we cannot know what could be the ultimate impact on our life, because the day is not very far when AI will take life-saving decisions. So due to such practical consequences, legal landscapes are fast moving across North American and European countries. In particular, for example, in Europe, we have with general data protection regulations. So European Commission is basically trying to regulate the use of AI. So unless clear logic that has been embedded or used in order to provide automated decision making for credit rating or in healthcare, for example, is simply not allowed. So with this, explainability, fairness, and accountability of an AI system is not only some desirable properties, but also increasingly becoming legal requirements. So question is, what is inside a black box model? So usually when we train machine learning algorithms, for example, in this case, if we want to develop an image recognition model, for example, what we do is basically we train a machine learning algorithms on thousands or millions of images, then we get a model. Now once we have a trained model, it can be embedded as web applications or maybe a mobile device where the trained model can be used to make predictions on unseen data. So during the training phase, if the internal working principle or the parameters are not known or hidden to the humans, for example, then these models could be completely black boxes. So we literally don't know how certain input instances were mapped into certain outputs, for example. On the other hand, if the internal functioning like parameters or the knowledge is transparently known to the users, so we call them interpretable model, for example, like decision rules or rule-based systems, linear models like logistic regression or linear regression, they are inherently interpretable, and we can transparently see which factors cause certain decisions or the outcomes. Now question is, what is inside a black box model? So inside a black box models, there are weights or activation functions or some sort of mapping logic. So we know that these mapping logics are basically generated based on a set of mathematical equations. They are chained together in order to understand the mapping between inputs and the outputs. But if you see, comprehending such a very complex mathematical equation is simply beyond the capacity of human. So in interpretable machine learning, there are two very important terms, interpretability and explainability. So what is interpretability? So interpretability is the ability to determine within machine learning systems or in AI systems the cause and effect. So like our credit rating example, for example, usually bank would compute the repayment capability, let's say based on customer John's income and amount. Then if the repayment probability is above a certain threshold limit, so they will decide whether to accept his loan application. Now explainability in this regard is that the knowledge about what features learned during the training of such a credit rating model. So for example, we can provide based on the relations the model learned. So we can provide an explanation saying that given your income, you are asking to borrow 50,000 euro, which is simply we think that too much, and we afraid that probably you won't be able to repay. So your loan application has been denied. So such explanations can be provided in both globally or locally. So global explanation means suppose we have let's say 10,000 instances that were trained to train the credit rating model. Now global explainability is about explaining the global behavior of the model. On the other hand, local explainability is about explaining individual decisions. So considering the drawback and practical and legal consequences, so this research tried to solve a very general problem, but with a focus of cancer diagnosis. So we asked how to improve both interpretability and explainability of a black box machine learning algorithms, thereby keeping a balance between accuracy and interpretability, because there is a clear trade-off between accuracy and interpretability. So, and provided the explanations that are backed by the domain knowledge. So in order to solve this problem, we conceptualized this problem across 4 different research questions. So the first research question is how to use different types of data, because we know in order to provide cancer diagnosis, we might have to combine different types of data together in order to provide meaningful, reliable decision. So the second research question is how to interpret and score the black box model. So we already know what contains in the black box model. So once we know what are the relevant factors that are actually forcing the model to make a certain predictions, we can highlight globally important features or factors in order to provide global interpretability. So the next research question is how to provide human understandable explanations of the decisions, because we need to generate explanations in a way so that human can comprehend or understand. The next research question we solve is how to validate the decisions that are backed by the domain knowledge or expert knowledge that could be coming from a knowledge base, for example. So in order to solve such a research question, so we have to tackle several problems, because existing approaches could not solve many problems. So the first problem is due to the nature of high dimensionality, multimodality, and dynamic nature of this domain. So majority of the approaches use limited data modalities. So for example, they utilize either multiomics data or one of the imaging modalities such as X-ray or CT scans, but not all the modalities are utilized properly or together. On the other hand, there are many external and reliable sources from which we could potentially extract a large-scale knowledge, for example, from scientific articles, metadata, and knowledge bases that are mostly ignored, but that could be properly utilized. So the second problem is high accurate deep neural network architectures are not only predominantly black boxes, but also they are very, very large. So they are really not suitable to provide inferencing in real time. So existing approaches try to solve this problem by applying different model compression techniques. So in particular, knowledge distillation process, pruning techniques, and quantization methods are used in order to get a lighter version of the model. So for example, the knowledge distillation process is about creating a student model based on the teacher model in order to approximate the behavior of the teacher model. But problem with this approach is that the underlying structure of a teacher model is remain the same. So we cannot significantly reduce the size of the models. And if the teacher model is a neural network architecture, so the student model has to be a neural network architecture as well. So as of quantization, we lose some precision. So these approaches are really not suitable to provide or to perform inferencing in real time. So in order to mitigate such problems, so several interpretable machine learning approaches, methods, and libraries have been recently proposed that can be categorized into 3 groups. So first group is probing technique. Probing means inspecting some or shedding some light in order to understand what is inside or what's the inner principle or the logic that were trained to train the machine learning model. So it is about understanding or exposing how important a certain feature is with regards to certain predictions. Second category is perturbation technique. Perturbation technique is about making minor changes into this data and see whether the model or the black box model is sensitive enough to making such changes. The third category is called model surrogation technique. So this is about creating a lighter version of the original black box model. So with the hope that this is inherently interpretable. Now using that surrogate model to provide global explanations. So we have so many interpretable machine learning techniques, but that can be utilized in 2 different ways in order to improve the interpretability. So the first approach is we simply build an inherently interpretable machine learning models and using that interpretable model to explain the decisions made by the machine learning algorithm. But as we know that in interpretable model might not be able to understand the level of the complexity, or maybe may not be able to model higher order interaction. So using interpretable machine learning model at first base may not be the viable option. So this approach is called anti-hoc interpretability. So the second category is, this is actually more desirable, is that first we train a black box models, then we apply different types of interpretability techniques in order to improve their interpretability. Then we get an interpretable model, now using that interpretability model to explain the decisions to the end users. So this is called post-hoc interpretability technique. But depending on the complexity of the level, we might have to combine both anti-hoc and post-hoc interpretability techniques in order to not only create the lighter version of the model, but also to improve the interpretability. So existing approaches did not combine both of these approaches together. So in our approach, we handle this by combining both anti-hoc and post-hoc interpretability. So another critical limitations of existing interpretable machine learning techniques is that there are so many different ways to explain the decisions to the end users. So the very first approach is using plot or charts. So we can see that using a plot or charts, this is very suitable for a domain expert like data scientist, or maybe someone from machine learning background, but this is really not suitable for the non-domain experts like patient. So there is another approach is called additive feature attribution. So we can see that some features, for example, monthly income, employment status, are positively impacting the decisions. On the other hand, some features like credit rating history, which is bad in this case, is negatively impacting the outcomes. So the third approach, it is actually desirable and suitable for the non-domain expert, is providing the explanations in terms of decision rules. Since decision rules contain simple if-then structure, so it semantically follow how humans tend to think. Additionally, we might have to provide constructive explanations. Suppose the original decision in John's case is denied. Now, if John asks for further clarification or constructive query, for example, could you please tell me why it was the case, why my loan application has been denied, why it was not accepted? So in that case, so we can think about providing constructive explanations, saying that, look, given your current income of 3,000 euro, so and having a bad credit rating history, your loan application has been denied. So now, in order to improve the chances, you might have to increase your income up to 1,000 euro. Then there is a high chance that your loan application will be accepted. Another problem with these existing approaches is that they lack of validation and reasoning capability. So far we talked about deep neural network architectures and other models. So they largely fall in connectionist AI paradigms. So because they are largely interconnected, and also inspired by how human thinks, like artificial neural networks. But they don't have the capability to answer follow-up queries. For example, for this case, if I ask the connectionist deep neural network architecture, whose picture is this? So since this connectionist AI has high predictive power, this is more likely that it would be able to tell us that this is a man. But if we ask them why this is a man, this connectionist model won't be able to answer to this question, because I trained this image recognition model based on a bunch of images, and no domain knowledge were really incorporated into this model. But in our cancer diagnosis use cases, patient could have other questions. For example, how did the model reach to this decision? Whether the decision is actually reliable, and how do you know that the decision was not biased? Did you take the algorithmic fairness or other aspects into consideration? So connectionist AI cannot answer to this question. But the positive advantage of connectionist AI is that they have very high predictive power, so we cannot, but since they cannot simply, black box models cannot simply provide the explanations in a transparent way, so it makes the overall knowledge acquisition non-transparent. On the other hand, a symbolic AI module, for example, if we have a properly structured knowledge graph or knowledge bases that are coming from reliable sources like scientific articles or knowledge bases, then using a semantic reasoner is a small software which is able to understand the relations between different concepts in a knowledge graph. would be able to generate answer to these questions. For example, I recognize a person, and all I know from this knowledge base is that a person could be either a man or a senior. So I infer the type person based on the facts present in the knowledge graph. So I'm very confident that this is a man. So in order to introduce such a capability into the model, so we might have to go for knowledge graph based reasoning technique. So this is technically a neurosymbolic AI by combining symbolic AI and connectionist AI. But problem is that this is really difficult to train a machine learning algorithms which is highly accurate and highly interpretable at the same time due to the trade-off between accuracy and interpretability. So we try to mitigate this by keeping a balance between accuracy and interpretability, thereby not to lose the significant accuracy, but taking the explainability of a machine learning algorithms to the maximum extent. So now I start the journey with building accurate machine learning model. So since our data is very, very high dimensional, for example, omics data, so they could be usually more than 20,000 dimensions. So within this very high dimensional data, existing approaches like PCA is simply not able to, are less effective at understanding useful representation. So current approaches are increasingly relying on autoencoder based representation learning techniques. So using an autoencoder, the encoder module embeds the input into lower dimensional vector space, and the decoder module reconstruct from the latent space the original representation. Then the representation can be extracted from this bottleneck layer. So this bottleneck layer is basically controlling how much information needs to be passed or propagated from encoder to the decoder, so that the decoder would be effectively able to reconstruct the original distributions of the data. We can see that by projecting into a lower dimensional vector space, which has significantly lower dimension than the original data, we are already able to handle the curves of dimensionality. But oftentimes, using only one type of data may not be suitable. For example, in our cancer diagnosis use case, we might have to use biomedical text, imaging data, as well as omics data together in order to learn a multimodal representations and provide a single outcome. So multimodal information fusion techniques is getting emerged, so which is about learning useful representations from different types of data and combine and projecting them into one place, so that the representation could be used for both supervised and unsupervised learning tasks. So the advantage of such a paradigm is that if one of these modalities is missing, the system will still be able to generate predictions or solve the problem at least to some extent. However, this approach is called shared latent representation, and it has a potential limitations, which is the reconstruction loss, which we could expect from this bottleneck layer, is significantly higher. So, so in many situations that we observe is that this shared latent representation learning is simply not very effective due to higher mean reconstruction loss. So in our approach, we built a latent representation learning techniques. So the idea goes as follows for three different modalities. So first we learn representation from the individual modalities and project them into lower dimensional vector space, then optimize the reconstruction loss for individual modalities. Then we project all the modalities, concatenate all the modalities here with C. So this approach is called latent representation concatenation. So our empirical study found that the reconstruction loss for such a network paradigm is significantly lower to what we observed for the shared latent representation learning techniques. So useful advantage of this approach is that once we know the concatenated vector space, so this can be used to solve a classification problem. In particular, if we just simply add a fully connected softmax layers, it should be able to generate predictions. So for our case, we could provide cancer types predictions. Okay, so in order to assess how well this approach compared to other unimodal and black box models, so we performed some experiments. So for this experience, we used three types of multiomics data: copy number variations data, gene expression data, as well as microRNA expression profiles. About 10,000 patients from Pan Cancer Project, covering 33 different types of cancer. So additionally, let me tell you that there are only two types of genes that are considered for this fishery space, which is oncogenes. So oncogenes are mostly responsible for different types of cancer that we know, and protein coding genes are actually simply genes that they are mostly not responsible for different types of cancer. So we know that within such a very high sparse fishery space, we really needed to apply representation learning techniques beforehand. So in order to provide fair comparison with existing approaches, we trained both unimodal models as well as multimodal models. So as of unimodal models, we trained TabNet, which is very known to effective for tabular data. We trained multilayer perceptron as well as gradient boosting freeze on the projected PCA and ISO-based projection space. As of multimodal models, we compared our approach, which is latent representation configuration techniques, with shared latent representation learning techniques. So we train each of the model on 80% of the data, and we evaluated the trained model on 20% of the held out test set. In terms of precision, recall, F1 score and Matthews score relation coefficient, given that our data set was slightly imbalanced. So I try to avoid the very details of the results, but let me tell you that our approach significantly outperformed other approaches. Additionally, the misclassification rate was minimized significantly, in particular for certain cancer types. For example, for thyroid cancer type, prostate cancer types, rectum, adenocarcinoma, and cancer of bile ducts, our approach managed to reduce the misclassification rate up to 10%. So this is a significant improvement, because existing approaches were literally struggling at differentiating these cancer types because of the nature of the data. Although our approach has some drawback in a sense that the misclassification accuracy was increased, misclassification rate was increased up to 1%, between 1 to 5% for selected cancer types such as kidney cancer or colon cancer. Since our approach is consistent across majority of the cancer types, so this is a higher indication that our approach is likely to have higher generalization capability, because oftentimes we really don't need a very fitted model. All we know is that we need a well-fitted model, and it should be able to provide reliable predictions even on unseen data. So now that we build black box models, we start by interpreting black box model. So I personally experimented with so many different interpretable machine learning techniques in order to improve the interpretability for both unimodal and black box models. So for this talk, I will be mostly talking about self-attention mechanisms that I basically improved as a basis of the improvement. So the basic idea of self-attention network is the core, or the key is the attention mechanism. So the attention mechanism, what it does is basically perform pairwise sum across all the inputs that we have in this input space. Then it generates the attention weight vectors, providing a relative importance across individual input instances that we have. Then it generates attention vectors in the product layer. Then the attention vector is basically feed into a softmax layers in order to normalize the value between 0 and 1. And then, based on the attention weight vector, they decompose the feature importance by ranking the features based on increasing or decreasing order of weight values. So this way we could improve the interpretability. But problem with their approach is that their attention mechanism simply applies directly on the original feature space, as we can see by putting less emphasis on the curves of dimensionality. So in our approach, we solve this problem by applying attention mechanisms on the modality specific and cross modal specific latent space. So now that with autoencoders we managed to handle the curves of dimensionality, but this space latent representation part is basically not interpretable. So how to interpret this part? So we interpret this part in 3 steps. So first we record the maximum when we perform the max pooling operations, for example, using a convolutional encoder. So here this is an example of how we record the maximum as well as their locations. So this is, it showed an example of 3D max pooling operation on a 2x2. We have another global attention layer which should be able to provide and generate the global feature importance. So now based on the same experiment settings that we had previously, so we identified globally impactful features, so both globally impactful features, so that can be conceptualized in both ways. For example, these features are most impactful genes in a positive sense, that these genes or features are actually contributing positivity to the overall behavior of the model. On the other hand, these genes are negatively impacting to the overall decisions, so these are least impactful genes. So if we consider these most and least impactful genes, we can already consider them as a top K feature space. So now that we build a black box models, interpreted it, and identified globally important features, so the next step is model surrogation and explaining decision rules. But why do we need to explain in a more intuitive way? Is that, as I already argued, that plots are simply inefficient for non-domain experts like a patient. So our solution is using rule-based and textual-based explanations, which simply follow if-then structure and largely resembles how humans tend to think. But additionally, we might have to provide constructive explanations, like the guy John, who applied for a bank. He additionally expects constructive explanations. So we combine counterfactuals and feature attributions with the original decision rules that we have generated. So the next problem remains is that AI systems, according to EU GDPR, an AI system needs to be queried multiple times in order to reconstruct the logic. But since our black box model is very, very large, so it is a high indication that we may not be able to generate predictions in real time. So not only it will tend to high inferencing time, but also it will take a lot of memory. So the memory usage would be higher as well. So in order to solve this problem, so we find a subdomain of the original feature space, like we already talked about top K feature space, and generate a student surrogate model of the subdomain space. Okay. So since the objective is training a smaller, faster, and student surrogate model, so we hypothesize that if we train a surrogate model which is inherently interpretable on the top K feature space, then it would be sufficiently approximates the behavior of the teacher model, and thereby we will end up with a lighter version of the model which can be used for real-time inferencing. So for this, we got top K feature space, then we trained different tree-based and their ensemble techniques. Now, in order to mitigate bias variance trade-off, so we perform stacking ensemble of different tree-based surrogate models before finally extracting decision rules and the counterfactuals from the base surrogate model. So first, we extract decision rules. So now, in order to extract the decision rules, so we simply follow from the root node, we traverse until a leaf node containing the decisions. Now this split is based on some splitting criteria such as information gain or entropy theory, so that the node that satisfies this splitting condition. So we simply traverse from root node to the leaf node, thereby we generate the decision rules. So now, in order to generate counterfactuals, so we keep the internal architectures of the surrogate model to be same, but we make minor changes into some feature space, in particular in our top K feature space. And so these minor changes is called W perturbation. So we change minor values to our input X, for example, with the hope that the predictions would be changed. So if the prediction is changed or flipped up into completely different predictions, so it would be our model would be able to provide counterfactual explanations. But also there is a possibility that if we make changes across individual feature values, at least the behavior of the model would be changed in terms of probability distributions over the classes. So now that we generated a surrogate model, can we confidently say that a surrogate model can be used instead of a black box models for solving or maybe in a real life? So in order to assess, we compare the predictions made by a black box models and a surrogate model. So how we did it is basically we compute R-square measure. So R-square measure can be interpreted as the percentage of the variance captured by this surrogate model. So for this individual surrogate model, we generate the predictions, Then we compare their simply sum of square errors. Now, how to interpret this R-squared measure is that if the R-squared measure is close to 1, that means the student surrogate model has managed to approximate the behavior of the black box models to sufficiently. So in that case, a surrogate model can be used instead of black box models. On the other hand, if R square is close to 0, which is a strong indication that the surrogate model is simply failed to approximate the behavior of the preset model or the black box model, so we should not use such a surrogate model for providing clinical diagnosis, like in our case, the cancer. So we performed several experiments, but I try to minimally cover it. So first, we qualitatively analyze the quality of the rules in terms of confidence and fidelity. So as of copy number variations modalities, so we achieved the confidence and fidelity score between 88 and 89%. So thereby the copy number variation data is simply not suitable, maybe in order to provide more reliable decisions. On the other hand, gene expression data, for the gene expression data, the confidence and the fidelity scores are between 90 and 92. So the potential reason could be that copy number variations data does not contain sufficient signal in order to differentiate between different cancer types or classes. On the other hand, gene expression data might be more suitable, so the quality of the rules are significantly improved. On the other hand, in order to provide quantitative evaluations for the predictive power of the surrogate models, so we compute the R-squared measure for all the previous models that we have generated. So as of copy number variations data, we can see the R-squared measure is slightly above 86%. So on the other hand, for the gene expression data, the R-squared measure went up to slightly above to 94%. So considering that we got up to 96% accuracy for gene expression modality using our black box model, so it indicates only 1.5 to 2% accuracy drop compared to our black box model. So we can say that unless there will be lot of misclassifications happening during the inferencing time or during the evaluation phase, so we could potentially use this extremely randomized tree model instead of surrogate model, instead of black box model. So to give an example, how decision rules and associated counterfactuals as well as additive feature attributions approach could help to generate or achieve human interpretable explanations. So let's consider that for a patient we have a gene expression profile like this. The expression values across different genes, and the original target class is breast cancer. So now, by combining the rules and a set of counterfactuals as well as feature attributions, we can provide the more reliable explanations. So as we can see from this list, is that for the original decision, breast cancer, our model has predicted breast cancer, where this feature had certain values above a certain limit. Additionally, we generated a set of counterfactual rules, thereby showing that a single decisions can be arrived, or we can arrive at a single decisions based on different splitting or different combinations of the input values. So for this, although we had 33 different types of cancer, so we conceptualized this thing for the most probable classes based on the probability distributions of the classes. Now, if we take a look at the feature attributions, so we can already see that some features are positively impacting in favor of the original decision breast cancer. On the other hand, some genes are negatively impacting the counterfactual decision, which is colon cancer in this case. On the other hand, if we would use a single rule-based explanations like anchor, so we would end up with a single rule, and we would not be able to provide neither constructive explanations nor the feature attribution-based explanations. So this is clearly outline the significance of combining different types of explanation-based technique in a single place. But question is that we provide the decision rules and counterfactuals, as well as we highlighted what are the most important antecedents that are present in the decision rules. So far, we have no idea whether those identified features or biomarkers are really biologically or biomedically validated or significant. So so if that's not the case, that the model won't be able to provide the validation, won't be able to validately say that the generated rules or all the biomarkers of the genes are simply backed by or supported by the domain knowledge. So in order to solve this problem, our approach proposed a solution called evidence-based explanation. So now that we already had the decision rules and a set of counterfactuals, so we simply extended the domain of these rules by introducing a theory of background knowledge. So that semantically follows a background knowledge graph, for example. So for this, we had combined different types of facts about individual biomarkers, like for example, biomarker type. I already mentioned about having oncogene and protein gene. Additionally, we could conceptualize what sort of evidence do we have, whether the evidence is coming from PubMed or cancer or MASH, or for example, whether a certain biomarkers or feature is significant with respect to, let's say, different types of cancer. So whether a single biomarker is not only responsible for only one type of cancer, but also other types of cancer, as well as how many scientific articles have supported this evidence. So if we have a domain knowledge graph, for example, using a semantic reasoner, we can potentially reason a query about an individual biomarker and get the evidences in a more transparent way. So what are the requirements in order to develop such evidence-based explanation is that we need a connectionist model. So now that we have both black box model as well as the surrogate model, so this requirements is already fulfilled. Now we need to develop a domain-specific knowledge graph and an ontology. Then we also additionally need a semantic reasoner as well as an explanation module, so that this explanation module would be able to combine the decision made by connectionist module and the reasoning which is being generated by semantic reasoner. So first we collect all the past evidences. For this, first we develop a domain-specific ontology, which we are calling on-component ontology. So for this ontology, we rely on existing ontologies. So this is one of the best practice in the area of semantic web. So using that domain-specific ontology, so we already extracted this information from different sources, and then based on this ontology, we form a knowledge graph. So the knowledge graph represents semantically structured facts about cancer diagnosis, for example, or it could be also applicable for other domain as long as we have enough evidence. So then all the facts can be represented as a triplet. So as you can see from this figure is that biomarker and cancer are subject and object respectively, who are responsible for indicates the relations between biomarker and cancer, saying that a biomarker is typically responsible for not only one, but it could be different types of cancer. So if we have such facts present in different structured sources, like in scientific articles, so if we have a example like this, that all oncogenes is responsible for cancer, so PP53 is an oncogene. So then we can deductively conclude or entail from following the background knowledge is that PP53 is responsible for cancer. So we can extract such relations in the form of triples and integrate our domain knowledge graph. So we can already see that these are already discrete symbolic representations about the knowledge about cancer genomics. So this discrete symbolic representation then can be used to infer the relations between a biomarker and its association with respect to different types of cancer. So additionally, we might have to enrich the domain knowledge with additional knowledge. For example, so far I talked about protein coding genes and oncogenes, but there are some genes that have both oncogenic and tumor suppression functionality. Those are called proto-oncogenes, so short for POTSF. So we might have to extract such a meaningful, such a reliable information from scientific articles. So, for example, if we have a knowledge or some abstract contains such information that TP53 and APS are top POTSF genes in terms of number of scientific articles and their associations with how many different cancer types, then we need to extract such useful information and enrich our existing knowledge graph. So for this, we employ transfer learning settings. We train two domain-specific transformer architectures, w.r.t and sci.r.t, on a recent articles that are published between 2019 and 2021. So you might be wondering why I'm considering only recent articles. Is that so far all the rules and the predictions made by the algorithms are basically generated based on a set of mathematical and statistical learning theory. So far we don't know whether they are really biologically validated, but since this domain is quite evolving and dynamic, so new findings are being already published more or less every day across different databases. So our database may not be quite up to date. In particular, the data that I used for training the model was published in 2017 in the Cancer Genome Atlas. After there has not had any additional release. So on the other hand, the scientific articles now contain more up-to-date information. So there is a potential chance of concept drift. That means my model is maybe able to provide reliable diagnosis decisions for the present scenarios, but it may not be up to date. So we should not rely on the predictions made by such an algorithms. So we trained this named entity recognition module. Then after identifying the relations between those biomedical entities, we extracted them as a RDF triples and combined them into our knowledge graph, yielding about 0.5 million triples. Okay, so now that we have all the components ready, so having now all these components ready, this is the overall approach, neurosymbolic AI approach. So as we can see that here, the connectionist AI module, it could be either a black box or maybe an interpretable surrogate model is able to generate the predictions. Then we don't simply let or use that predictions in order to provide explanations. Rather we validate the findings based on our domain knowledge. So where the symbolic AI module is actually providing that reasoning or the validation part. So once we know the predictions as well as validation from both connectionist AI module as well as symbolic AI module, finally we combine them together in order to provide the explanations in a more human interpretable way. So how does the reasoning work? So for making the reasoning work, we had to follow two steps. In the first steps, we instantiated a semantic reasoner based on the facts that are present in our knowledge graph in a closed world assumption settings, because we assume that our knowledge graph is detectably closed and we have this is complete and there are no consistencies into our knowledge graph. So the next step is basically entailment. Entailment in a sense that for a given information like a gene like TP53, we ask query to our neurosymbolic AI module, what's the underlying reasoning why a certain genes like TP53 is responsible for breast cancer, not for colon cancer. So we did this entailment in two steps, in two ways. So first we ask or send a query in description logic axioms format. So since a semantic reasoner is inherently able to understand the description logic axioms, so now it should be able to infer the association or what's the relations between Ph.D genes, for example, with with breast cancer, whether the significance is high, whether we have enough evidence from PubMed. So, but problem with description logic axioms is that the expressivity is limited. So we had to employ another method, which is abstract meaning representation. So it goes as follows. So we have a natural language questions, so which is simply a medical doctors could write in their own language. Then this module, abstract meaning representation learning techniques, can extract what can understand the context, as well as it understand what are the biomedical entities based on the context we are talking about. So then it aligns the context of the biomedical entities with all the facts that are present into our knowledge graph. Then it understands the linking before sending it to the semantic reasoner part, and the semantic reasoner would be able to generate explanations or the reasoning in a more transparent way. So to give you an example, suppose we are asking which Ph.D biomarker is responsible for breast cancer, which has high significance, as well as we have PubMed as evidence. So to understand this part, we simply follow this reasoning path. Suppose we are talking about this guy, and all we know that this is unknown type. We don't know which biomarker we are talking about. So all we know that this is a biomarker. So we simply follow this path, and it should be a POTSF type. The oncogene type is POTSF. Then this is responsible for breast cancer, and breast cancer is one type of cancer, and the significance is high. And we, what's the evidence source? Source of evidence is PubMed. Then if we simply follow this reasoning path, the reasoner would be able to provide answer. For example, this below figure shows an example in description logic rules. So we can transparently see that TP53 is a biomarker. It also has protein genic nature. It also has proto-oncogenic nature. So it has high significance with respect to breast cancer, and as much as 493 scientific articles have supported this evidence. Okay, so now that we have the decision rules, reasoning, as well as counterfactuals, and additionally we have additive feature attributions. Now by combining all of these predictions or the reasoning part, we can now generate a textual-based explanations before sending it to the medical doctors as a recommendation. Then a medical doctor could combine his own expertise, domain expertise, and combine the textual-based explanations before explaining it to the patients in a more interpretable way. For example, he could potentially explain saying that breast cancer is recommended for your case because there is one blood biomarker, TP53, is present in your body, and this is a protein coding gene, and it is one of the most significant genes, and it has very strong mutation association with respect to breast cancer, and as much as 493 scientific articles supported this evidence. On the other hand, for your case, lung cancer was not recommended because although only one blood biomarker, FLT3, has been found that is relevant to your case or as important features, but there is no scientific publications that support this evidence. Okay, so now that we have trained our black box models, we have interpreted, generated decision rules, as well as we have validated the findings based on the domain knowledge. So finally, we did some experiments in order to measure the explainability. So in order to measure the explainability, we rely on two sources called system causality scale. So this is just like from more social point of view. So we have a explainable user interface. So we asked some volunteers in order to know or judge up to what extent the provided explanations based on this user interface is actually meaningful or helpful to the users. So as much as only 54 participants responded. So there are some questions. For example, I understand the explanation very well. I didn't find any inconsistencies. Now, based on the response from 54 users, so we received a system causality score of 0.88. That means about 88% users were really satisfied. But due to time restrictions, I'm not discussing more about how the sufficiency and comprehensiveness scores were calculated. But all I can tell you that these are inspired by the natural language processing. And for this, we generated the rationale, for example. So the rationale means which rationales or up to what extent that supports our evidence. So we additionally computed this sufficiency and comprehensiveness score. So to summarize, in this approach, we have tried to improve both interpretability and explainability of a black box machine learning algorithms, thereby keeping a balance between accuracy and interpretability. So what I can tell that using a set of novel interpretable machine learning approach, and by validating our findings based on domain knowledge, we were able to not only to improve the accuracy, but also to keep and take the explainability into maximum level. So as we can see that for the black box model, for gene expression modality, it shows 96% accuracy. Now compared to this approach, our approach for the same gene expression modality, the best surrogate model, extremely randomized tree, achieved an accuracy. So accuracy now, I mean, in terms of F1 score, 94% score. So considering this, we experienced only 2% accuracy drop. But in return, we were able to provide human interpretable explanations by combining with constructive explanations. So this research has made several contributions. For example, we not only prepared a multimodal data, but also we prepared a domain-specific knowledge graph and ontology. we train highly accurate black box models. Then for the black box model, by applying different interpretable machine learning techniques, we not only generated lightweight surrogate models, but also novel interpretable machine learning methods. Several scientific articles have been emerged from this. Source code, models, and web applications have been publicly open source for accelerating open research. So, in particular, 11 scientific articles have been emerged from this in top data science as well as top bioinformatics conference and journals. So one of my paper also got Best Paper Award in a top data science conference, and I received ICT Young Researcher Award 2020 in 2020 for my significant contributions to ICT-related research. So our approach also has several potential limitations. For example, we didn't go for clinical validation because our approach is basically data-driven AI approach. Although we took several strategies in order to improve the fairness, but improving the decision fairness was really not the main focus. But I can tell you that I try to mitigate both data selection, sampling biases, model selection biases, as well as prediction biases by employing ensemble learning techniques as well as other approaches. So in future, we want to mitigate these limitations, as well as we want to release the data as well as the models by complying with the fair data principles. We want to perform knowledge graph-based embeddings in order to infer new knowledge. So to conclude, we hope that our approach has managed to make significant contributions to science, and we also hope that our approach would be able to provide us contributions to increasing adoption of AI-assisted applications in clinical settings, but of course it needs rigorous validations and evaluation. Finally, I want to clarify that our approach is not to replace human oncologists, rather to help them so that they could combine their own expertise and get the recommendation from the model in order to provide more reliable decisions to the end user or to the patient. So finally, I would like to acknowledge my supervisors who had tremendous contributions starting to this journey, especially Professor Dr. Stephen Deckard, Professor Dietrich Repol-Schumann, Professor Dr. Michael Kushai, Dr. Uyabian. I would like to thankfully acknowledge my family and their contributions. I would like to thankfully acknowledge my non-profit colleagues, Informatic 5 colleagues, as well as Bangladeshi community in Germany. So thank you very much for listening.
Thank you.